Hey everybody, welcome back to the channel. So today I want to review through all of the general chemistry that you need to know for the MCAT. I got a 100 percentile in the MCAT about 2 years ago, and this was actually my primary source of studying was the Milesdown Review Sheets. It's a really fantastic resource for learning pretty much everything you need to know for the MCAT. I think it is very helpful to be able to put all the information together, know a little bit more additional information, structure all the information. And so that's what I'm going to do today is try to show you images and explain every concept so that you know everything you need to know for the MCAT. All right, how I'd recommend you get through this video is you pause, you rewind, you take notes, make sure you understand every concept as we're going through it, and I'll just be asking questions as we go along just to make sure that you understand the concept. And if you can answer the question immediately, then you probably know the concept. If not, then just pause the video and just keep going. So the first thing we need to know is what these symbols mean. And so the A is the mass number. The mass number is the number of protons and neutrons. And the Z is the atomic number. And this is kind of the number that defines what atom we're looking at. So that's the number of protons. Now, we can have isotopes, and isotopes is when there's a different number of neutrons. An example of this is carbon 12, carbon 13, carbon 14. Each carbon has 6 protons, which is, again, the defining feature of the carbon, the atomic number, but it has either 6, 7, or 8 neutrons, and so that will be the mass number, 12, 13, or 14. Now, if we take the percentage of the percentage of the carbons that are in the state of 12, 13, or 14, and we weight the averages of them. So if there's 99% carbon 12s, 0.5% carbon 13s, and 0.5% carbon 14s, then the weighted average is going to be very close to 12, just a little bit above 12. And so if we look at a periodic table over here, you can see that if I look at carbon, again, carbon, the mass number is usually 12, 13, or 14. The atomic number is 6, and the atomic mass is 12.011. And we get that number from averaging the sum, from summing up the mass numbers and multiplying them by the percentage at which they're found in nature. All right, so that's that. Now we're going to look at the scientist contributions. So the first thing is Rutherford model, and this is in 1911, and he basically did this really cool experiment where he found that he took these alpha particles, which were radioactive substances, and he shot them through a gold foil really, really quickly. And so what he expected is that almost all of the alpha particles would move just straight through this gold foil and leave a little print on this on the sheet over here. And so what we were expecting is that we see this little dot over here, and what he actually saw is that majority of the dots were right here, straight through, but we actually found that it deflected more often than he was thinking. Deflected 5% of the time. It doesn't really matter that you know the number, but he found that, this is what he was expecting, which was the Thomson model, which was the existing model, which is that, the atom is just this ball with a lot of different particles all around, but he actually found that there must be some solid mass in the middle that's resulting in this deflection. And this solid mass must not take up a lot of the space. It's mostly empty space and has a solid mass in the middle, and that's the nucleus. So that's what Rutherford figured out. Okay. The next thing is the Bohr model, which was actually just 2 years later. And he found out that, let's look at the Bohr model. So basically, he found out that these electrons exist in these energy levels, like n equals 1, n equals 2, n equals 3, and he tested this with hydrogen. And he found out that when an electron goes from an n equals 3 or an n equals 4, like a higher energy state to a lower energy state, it actually releases light. Right? And so he said that, the Rutherford model is correct, that there's a nucleus in the center and that there's these electrons that exist at energy states and they travel around the nucleus. And so that's kind of what the Bohr model said. And he said that photons are emitted, and when the electron goes from a high state to a low state, and photons are absorbed when an electron goes from a lower state to a higher state. And so this is actually pretty close to what the reality is. But what we ended up figuring out is that these electrons don't exactly live in this state, but it actually there's a probability model where an electron can exist in any area within a defined place. So it might be a sphere around the nucleus, and the electron can be found usually 95% of the time within that sphere. Or it might be like a p orbital, and you might find the electron 95% of the time within that space. But you can't actually know for sure where the electron is. And that statement that you can't know where the electron is for sure is the Heisenberg uncertainty principle, which is that you can't know the momentum and the position simultaneously. And I was always really confused by this concept, but somebody explained this to me really well, which is that momentum, you should just know, is where the particle is going, and position is where it is. And so if you can basically take a snapshot of the atom and you can figure out where is the electron right now, but you can't also know where it's going. And so that's why the Bohr model is incorrect in that specific case where you don't actually know that this electron is going like a planet in a circle around the sun, around the nucleus. Actually, there's just a probability that you know that it's probably going to be within the space, but you don't know exactly where it's going to be at any given moment. And you can't, if you do know that, then you can't also know where it's going to go. And so that's kind of the Heisenberg uncertainty principle. How I think about it is if you had a camera and you're taking pictures, you can know where it is, but you can't know where it's going. And simultaneously, if you know where it's going, you can't know where it is. Okay, the Hund's rule, and I'm going to open up the periodic table again. Hund's rule is, let's say we take something like nitrogen, right? Nitrogen has two electrons and it's S1s, two electrons and it's 2s, and then 3 electrons and it's 2p. We'll get through this a little bit later, but just stick with me. And so we know that there's 3 electrons, and it's 2p orbital. And if there's 3 electrons in the 2p orbital, what Hund's rule says is that all 3 of the electrons are not going to be in the same space. It's actually going to fill up, like if we, I'm just going to go down a little bit. If we look at, but okay, we'll get to it later. But if we basically look at how the electrons are distributed, what we'll see is that it's kind of like these electrons are distributed within the 2p. So each one takes one of these little orbitals rather than both of them pairing up in the orbital before taking up empty space. This is because electrons don't like to be together, they repel each other, and so they only start to fill up again once there's a 4th, 5th, or 6th electron within this 2p. I hope that makes sense. Okay, the last one is Pauli's exclusion principle, and we just say that no electron has the exact same 4 quantum numbers. That's basically what Pauli's exclusion principle is. And so obviously we have paired electrons in these 2p, 3p, 3d, in all these orbitals we have paired electrons, but we say that the paired electrons, one of them must be a +1/2 and the other one must be a -1/2. This is kind of just a convention thing, but that's kind of what we call the spin on the electron. Okay, there's some constants that you need to memorize for the MCAT. The first one is Avogadro's number, which is 6.022 times 10 to the 23rd. The second one is Planck's, which is 6.626 times 10 to the negative 34. And this third is speed of light, which is 3 times 10 to the 8th. And you don't actually need to know 6.022. You kind of, if you know 6 times 10 to the 23, that's fine too. Make sure you know what the units are. So Avogadro's number is just a number. You don't actually need, there's no units to it, but we say that that is equal to 1 mole. So when we say 1 mole of carbon, what we're saying is that we're taking 6 times 10 to the 23 atoms of carbon. If we say Planck's constant, you kind of just need to know 6.6, but it's good to kind of, I just know all the digits because they just keep showing up in questions. But for calculation purposes, if you just know the 6.0 or 6.6, you're probably going to be good in terms of the MCAT. These are also equations that you should memorize, not too difficult. They're both actually the same equation, E equals HF. And we know that frequency times wavelength is equal to speed. And so we know that the speed of light is, and so if we know what the frequency is, we can figure out what the wavelength of that light is, and if we know what the wavelength is, we can figure out what the frequency is. Okay, this is Planck's constant, so if we multiply Planck's constant by the frequency, we get the energy. And again, if we take the speed of light and divide it by the wavelength, we get the frequency. So these are just the same equations. Okay, the next thing we need to know is quantum numbers. Quantum number is 4 different terms for defining what an electron is. That's orbiting the nucleus. The first thing is the principal quantum number, and it labels what shell number or energy level that the electron exists in. So the electrons in hydrogen and helium are in the first principal number, or the first energy shell. The electrons in nitrogen, for example, which is what we were looking at before, is in the second energy level, and you can kind of see that you can see what the energy levels are. So the first number here, 3, this 3D, everything here is in the third energy level. Okay, the next one is, also I guess another thing that you should know is that usually these match up with what row they are. That is true except for these D and F. So 2S and 2P are in the second row, so you can kind of know what the principal number is. But from here, it starts at 3D, even though it's in the fourth row. So you should just know that. Okay. Next thing is the L, which is the azimuthal quantum number. You don't actually need to know these names, but you should know what these letters are. And this is the 3D shape of the orbital. So this is what I was talking about before, is this is the probabilistic model for where you think that the electron is going to be 95% of the time. So if it's in an S orbital, then you know that it's going 95% of the time it's going to be within the sphere. And we can figure this out because if we take a lot of snapshots of the atom, we can figure out where's the electron 95% of the time. That doesn't mean it's always going to be there. Sometimes it might be way far away, but 95% of the time, the electron is going to be within the space. Same thing with P, it's going to be somewhere within this space. And D, it's going to be somewhere within that shape. I can't make it with my hands. And F, similar thing. Okay, so you should know that the possible values is between 0 and n minus 1. 0 refers to S orbital, 1P, 2D, 3F, 4G. You never really deal with G orbitals in the case of the MCAT, but you can go up to an F orbital. Okay, ML is the magnetic name, and that's when you get the orbital subtype. And the integers can be between negative L and L. So if you're dealing with a p orbital, you know that the p orbital is L equals 1. So the magnetic numbers can be between negative 1 and 1. So negative 1, 0, and 1. And you should know that each orbital subtype can contain 2 electrons. So that explains why a p orbital has 6 electrons, because it contains negative 1, 0, and 1, which is 3 orbital subtypes, and each orbital subtype contains 2 electrons. I'm going to repeat that again. So you can figure out how many orbital subtypes there are by taking the L. The L is dependent on which orbital you're looking at, and you can count how many orbital subtypes there are. You can multiply that by 2 because each orbital subtype has 2 electrons. And if you can do that, then you'll get the number of electrons that orbital contains. So let's take D, for example. D is 2 for L, so you know that the number of orbital subtypes is negative 2, negative 1, 0, 1, 2. So there's 5, which means that it contains 10 electrons. You can see that here, this is 10 long, which means that there's 10 electrons within the 3D orbital. Okay, the last one is the electron spin, and this is where the Pauli exclusion principle comes in, and that refers that for any one of the paired electrons within an orbital subtype, there has to be a plus 1/2 and a minus 1/2 spin number on it. Okay, these are some handy formulas. You can actually figure this out without knowing these formulas, so it's okay if you don't know it. But the maximum number of electrons in a shell is 2 times n squared. So in this shell this shell has a principal number of 2. So the electrons that it contains is 2 times 2 squared, which is 8. And if you count this, 1, 2, 3, 4, 5, 6, 7, 8, that's true. And if you do it for 3, you'd figure out that it's actually 18. And so if you do this, 2, 6, 8, plus 10, 18. Yep. So that's how you figure that out. And then the maximum electrons in a subshell is 4L plus 2. Okay, so we can figure out how many are in the D orbital, which is 4 times L, which is, what is L? L is 2. So 4 times L is 8, plus 2 is 10. So again, we figured out that there's 10 in here. All right. Pause if you don't understand anything. Make sure you understand everything. Yeah. And the next thing is a free radical. Free radicals are atoms or molecules that have an unpaired electron. Okay. Yeah, and then the next thing that we're going to talk about is diamagnetic and paramagnetic. This is actually a pretty simple concept, but a complicated term. Diamagnetic, all the electrons are paired, And it's if you have an external magnetic field, this atom, which has a paired electron, which has all paired electrons, is going to be repelled. But if you have one or more unpaired electrons, then it's going to be pulled in, and that's called paramagnetic. Yeah, again, follow Hund's rule. Hund's rule says that you double up only if all the electrons have filled up the orbital subtypes. And then you can figure out if it's paramagnetic or diamagnetic. So 1s2 is helium. Helium is right here. It's going to be diamagnetic because all the electron orbitals are filled up with both electrons. Now, carbon's right here, is paramagnetic because even though it has this 2 in this p orbital, you know that those those two electrons are in different orbital subtypes because of the Hund's rule. So make sure you understand that. Okay, the last thing is the Aufbau principle, and that just kind of says in which direction do you add the electrons. And so you can kind of, in which direction are you having n plus 1 value? So you can kind of go in this diagonal manner, 1s, 1 2s, 2p, right? And you can kind of go in this diagonal manner to know how do you write this. And so you know that, like for example, what's a good one to talk about? Okay, so this is a confusing one, which is that after 3p is not 3d, but 4s. And that basically tells you is that if you list all of these diagonally, the 1, 2, 3, 4, 5, 6, and you write S, P, D, F, and you go in this diagonal manner, and this is basically Aufbau principle, you can actually figure out what is the increasing energy levels. And so it's kind of confusing, but the 3D, according to this, is higher energy level than the 4S because right after the 3P is the 4S, and then you go to the 3D. Similarly, after the 5S is not 5P, but it's actually 4D. And so you can kind of figure out what is increasing energy levels based on these orbital subtypes. Okay, next we're going to go through the periodic table, which is a pretty important concept. It's actually very simple, as long as you kind of memorize a couple of things. So the first thing you want to know is what. And so you know that this is an alkali metal, hydrogen. These are all non-metals. I'm so sorry, erase what I just said. So these are all alkali metals, lithium through francium. The hydrogen is a non-metal. That's important to know. So everything in column 1 is an alkali metal except for hydrogen, which is a non-metal. These are also all non-metals, okay? The halogens are also non-metals, but they're the last column before the noble gases. So you should know that everything here are non-metals, right? If you look at my cursor, all the bright green, the halogens and the noble gases. The darker green are all metalloids, and I kind of remember what the metalloids are because they're kind of in a stair-step pattern. So the boron, the silicon, germanium, arsenics, I don't know what this is, right? But if you kind of go in a stair-step pattern here, you can, besides the carbon, you can know that these are all the metalloids, okay? All right, so again, these are all metalloids in the stair-step pattern. The carbon, the nitrogen, oxygen, fluoride, neon, all of these are all non-metals. The hydrogen is also a non-metal, sorry about that mistake. And all of these are alkali metals, okay, in this bright orange. These yellow are alkaline earth metals, and so these are all metals. These are also metals, we call them transition metals. And we call these post-transition metals, okay? Okay, so as long as you know that these pretty much are all metals, right? All of this, I'll use my marker. So all of this is metals, right? This is a non-metal. These are all non-metals. And this stuff is all metalloids. Okay. All right. Next thing is that these are all called rare earth metal rows, so you're not going to find them too often. A lot of them are actually only synthesized in the laboratory. And then this is actually pretty high yield important information. The effective nuclear charge is the pull between a nucleus and a valence electron. And so you can actually figure this out based on where in the periodic table you are. And so if you think about it, these are all pretty intuitive if you understand the concept, which is that the pull between a nucleus and a valence electron is going to be highest when you have the most protons in your nucleus, and the valence electron is the closest to the nucleus. So as you go down, right, as you go down, the valence electrons start to get further and further away because they're in higher and higher energy states, right? The N number is increasing. But as you go to the right, the number of protons in the nucleus is increasing, and the electrons are still staying at the same distance from the nucleus, right? So that basically defines all of these trends, is that generally as you go to the right, as you go this way, these numbers are going to increase. And they all kind of represent a very similar thing, which is kind of like this pull between the nucleus and valence electron. Now they have minute differences, and it's kind of useful to know these minute differences. The effective nuclear charge is how hard does the nucleus tug on this outer electron. And obviously something like fluoride is going to have a very high nuclear effective charge because there's a lot of protons in it, and it's not that far from the nucleus. Okay. The next thing is, how much energy do you lose, the ionization energy, when you lose an electron? When we rip out that electron, how much energy is being lost, right? And so, all right, I'm going to repeat that again because I made a mistake. So the ionization energy is how much energy does it take to make this atom lose an electron, okay? So if you're fluoride, it's going to take a lot of energy to make yourself lose an electron. The reason for that is because fluoride, again, has a very high effective nuclear charge. It pulls on its electron pretty hard. So it's going to take a lot of energy for this electron to be able to escape fluoride. Whereas this right here, I think it's, let's see, I think it's francium. Francium is down here where the proton number is relatively low, right? 87 protons in the nucleus, but the electron is pretty far away, right? You can see that this is 1, 2, 3, 4, 5, 6, 7 energy levels. So it's pretty far away. So this nucleus is not going to be able to pull on this valence electron that much. So it's not going to take a lot of energy to be able to rip this electron out of the atom. So that's why the ionization energy is low here and high here. Similar to electron affinity is how much affinity does an electron have, all right, I'm going to make a quick adjustment. So electron affinity is how much energy do you add when you add an electron into this atom. So if you look here, electron affinity is the energy change that results from adding an electron to a gaseous atom. So fluoride, the associated energy change is negative 328 kilojoules per mole. So to add an electron to fluoride, it actually wants the electron. And so this is a very important concept. So to continue, the electron affinity, when you add an electron, you can see that there's some energy that's released. And that energy is referred to the electron affinity, right? Okay, so why does it make sense that fluoride will have the highest electron affinity? Well, fluoride is just one step away from the noble gas, and so it really wants to get to this very stable configuration. And so it has a lot of protons. The protons are pretty close to the electrons, and so to add one more electron, they would really want that to get to this next level, to this noble gas configuration. Okay, so this is kind of important but a little confusing, is that the electron affinity is recorded as a positive value, even though that there's energy that's released when you gain an electron. Okay, the next thing is that electron negativity, right? And so electron negativity refers to the tendency of an atom of a given chemical element to attract shared electrons. And so when I was really confused about this when I first learned about it, but basically, if you think about it, if you have a bond between, I don't know, carbon and fluoride, which atom is going to attract that electron in the shared bond more readily? It's going to be the fluoride, because the fluoride has more protons that are closer to the valence electron that's in the bond than carbon does. So fluoride has the greatest electronegativity. And you can see that, noble gases don't have an affinity for electrons, and it would take energy to force an electron on them. And here, noble gases, none of them have electron negativity except for Kr and Xe. Okay, I hope that all made sense. If you kind of just remember that the general trend is this way for most of these, then you'll kind of just know what these values mean. Now, sometimes this is unchanged over here, but it's mostly important to, if you can just remember that most of the time fluoride is the highest, you can kind of remember these terms. Okay, the next thing to know is that the common electronegativities you can figure out is HCNOF, if you remember that, HCNOF, because they commonly ask these terms. You can figure out that they actually kind of jump by 0.5 every time. So if you start at 2 and you end at 4, you can figure out what these common electronegativities are. Remember, electronegativities is how much force does the nucleus of an atom exert in a common bond, in a covalent bond, right? So if you have HF, hydrofluoric acid, right? The fluoride, because its electronegativity is 4 and the hydrogen has only electronegativity of 2, you know that the fluoride is going to share a little bit unevenly and have most of that the electron pair over hydrogen, right? They're going to share, but they're going to share unevenly. So that's important. Okay, the only one that goes in the opposite direction of what we've been looking at is atomic size. So francium is generally going to be the biggest because there's the most number of protons. The electrons are furthest away, right? So that's kind of a bare minimum. Obviously, hydrogen is going to be pretty small because the electrons are pretty close. But francium is at one of the highest energy states, but the protons are holding it together a little bit less strong because there's only one proton in that for the outer shell, right? So you can kind of know that the atomic size goes in the other direction. The final thing to know is that cations are generally smaller and anions are generally bigger. The reason for that is anions is when you have extra electrons and cations is when you have extra protons, when you have fewer electrons. So yeah. And so if you have fewer electrons, there's going to be a greater tug. If you have more electrons, then the electrons might repel each other a little bit, but there's going to be less of a pull on them from the protons. If you have an anion where the electron is added to a new energy level, so a new shell, then it's going to be pretty big because there's going to be fewer protons and the electron is being added to a greater energy state. All right, I hope that all makes sense. The next concept is bonding and chemical interactions. All right, hopefully you're still with me. Now we're going to go through General Chemistry 3, which is bonding and chemical interactions. This is not too bad. Even the VSPR stuff, if you look at images, it's going to be a lot easier. The first thing is covalent bonds. Covalent bonds is when electrons are being shared between two elements, and usually there's similar electronegativity. If they're pretty high electronegativity, then it could be an ionic bond. If it's medium high electronegativity, it could still be a covalent bond, but it could be a polar covalent bond, which is that one atom shares it unevenly with the other and might steal it a little bit more. The example I gave before was hydrofluoric acid, HF, and that's a covalent bond, but that's a polar covalent bond because if you remember, hydrogen has a electronegativity of 2 and fluoride has a common electronegativity of 4. Okay. Usually electronegativity, it's polar if it's between 0.5 and 1.7. So I know I just said 2, but usually we say that it's ionic if it's like a metal and a non-metal rather than two non-metals. But you can see that it's usually between 0.5 and 1.7 is a polar bond. And non-polar bonds is when the electronegativity difference between the two atoms that are sharing the electrons is less than 0.5. So something like H2, it'll have electronegativity difference of 0, and so that's going to be a non-polar bond. Bond order, this is pretty self-explanatory, but if you have a bond order of 2, that means you have 2 bonds, a double bond, and the more that bond order increases, i.e. a double bond or a triple bond, it's going to have greater strength, it's going to have greater energy, and it's going to have less length. So the atoms are going to be closer together. So a triple bond actually holds the two atoms pretty close together. Coordinate covalent bonds always were confusing to me, and that's when a single atom provides both bonding electrons. So it could happen in Lewis acid-base chemistry, which is we're going to go into later. But it's kind of this unique situation because usually we think of covalent bonds as the two atoms sharing the electrons, but in this case, the one atom is providing both electrons to supply that bond between the two atoms, is supplying both the electrons. Okay, the next thing is ionic bonds, and so here is a good understanding of the bond type. Ionic is usually between a metal and nonmetal. Covalent is usually between two nonmetals, but you can kind of figure it out based on the electronegativity difference too. So if it's here, then it's nonpolar covalent. If it's here, then it's polar covalent, and if it's here, then it's ionic. Okay, ionic bonds are formed from the transfer of one or more electrons from one element of a low IE. Remember, this is ionization energy, and this low ionization energy means that when this electron is being released, how much energy has to be added. And so if it doesn't have that much ionization energy, that means it's pretty easy to get rid of it. To an element with relatively high electron affinity, which means that how much energy is released when you add an electron. And so usually this is when the electronegativity difference is greater than 1.7. Cations refer to positive ions and anions refer to negative ions. So positive ions are cations, and this is when electrons have been removed, and anions are when electrons have been added. It's important to note that cation doesn't mean protons have been added. Cations mean electrons have been removed. Crystalline lattices are when you have large organized array of ions. Okay. Intermolecular forces. Now this is pretty high yield. You can have hydrogen intermolecular forces. You can have dipole-dipole. You can have London dispersion. And van der Waals forces is a term that includes both dipole-dipole and London dispersion. Now it's important to know that covalent and ionic bonds, this always confused me for a long time, is within a molecule between atoms of the same molecule. Intermolecular forces is between two molecules, right? So let's say I have something like, HF and H2O, right? So these are two different molecules, right? And you can have this hydrogen bond between this hydrogen of the HF and the oxygen of the H2O. And so that is a hydrogen force, an intermolecular force. And you should know that it increases as you go up, right? So I want to give you an example of what London dispersion forces are. Dispersion force. Okay, and let's look at it. So London dispersion is kind of this interesting situation where you might have two heliums, right? And helium is usually it's what do you call it? It's noble gas, right? And so sometimes these electrons, remember that they're not in fixed positions, right? And so you might create this instantaneous dipole within it. And so you can sometimes, even though it's not a charged particle or it's not polar, you can have these redistribution of electrons that creates instantaneous dipoles, and that might create a very weak attraction or dispersion, and so that's attraction or repulsion, and that's called a London dispersion force. Now the next one is dipole-dipole, and dipole-dipole are basically a little bit stronger, and that's when you have two polar molecules, right? Remember, polar is when it's between 0.5 and 1.7. And so the polar molecule can create attractions or repulsions. And the attraction is going to be between the positive and negative components of one and the other. The repulsions is going to be between positives or negatives, right? So if you want to look at dipole-dipole, that example is hydrogen chloride, hydrogen fluoride, and water, right? So you can see that the chloride is partially negative, the hydrogen is partially positive, the fluoride here, and the hydrogen here. Now you should know that when hydrogen is one of those atoms that's involved in this dipole-dipole force, there's a special name for that, and that's called the hydrogen force. And so hydrogen forces are really types of dipole-dipole forces, but since hydrogen is so small, this is usually considered a special one because it's a little bit stronger than dipole-dipole forces. You should know that intermolecular forces are weaker than covalent or ionic bonds, right? And things like London dispersion forces are pretty momentary and instantaneous. Okay, sigma bonds refer to the first bond between something. Pi bonds is the second or third bond or the fourth bond, whatever, right? So a double bond is going to have 1 sigma and 1 pi. A triple bond is going to have 1 sigma and 2 pi. So if I'm giving you an example, I would tell you about CO, right? And so this has 1 sigma bond. Sorry, this should be CO, and that has 1 sigma bond and 1 pi bond. Okay, the next thing is formal charges. Formal charges are pretty difficult to understand, but let's say we take something like, let's look at an example real quick. Formal charge example, right? Okay, so formal charge is kind of like when you're looking at something like this, right? And so we give the when you have a bond, you give 1 electron to this guy. And when you have electrons, you give each electron to that guy, right? So the formal charge is this carbon has a formal charge. You can see that there's 1, 2, 3, 4, 5, 6, right? There's 6 bonds here. So we give 6, and there's no lone pairs here. So this has 6, and you know that normally carbon is supposed to have 4 because of where it is on the periodic table here. Remember, carbon is right here, and it has 4 electrons in its outer shell. And so it has 2 more electrons here than it's normally supposed to have. And so we'd say that the formal charge here is -2. Okay, let's do another example. Here, we'd say that basically, this is the formula. Formal charge is valence electrons minus dots minus sticks, right? And so here, if we wanted to figure out what sulfur should have, where is sulfur on it? Sulfur is right here. It should have 6 electrons, right? So 6, and we see 1, 2, 3, 4, 5, 6. So there's 6. And so this formal charge is actually 0 because it has what it's supposed to have. Let's look at this oxygen over here, right? This oxygen has 1 from this bond, and then 1, 2, 3, 4, 5, 6. So it has 7. And it's supposed to have, if you look here, it's supposed to have 6, right? 1, 2, 3, 4, 5, 6. And so this has a formal charge of -1. This also has a formal charge of -1. Here and here have formal charge of 0, and we said sulfur has a formal charge of 0. So in total, if I had to draw this, it'd be 0, 0, and 0, and then -1 here, and -1 here. And if you add all these numbers, then you get -2. And that's why you see a -2 here. Okay, I hope that was helpful. Just look at a couple of more examples if that doesn't make sense. Okay, the next thing is Vesper, and I think Vesper is kind of something you have to memorize, but it's not so difficult if you sort of look at a couple of shapes. So that's what I searched up here, and if you look at this, you can see that you can see kind of what the examples are. So a linear shape is kind of just a line. Trigonal planar is kind of like a triangle. Tetrahedral is kind of like a pyramid. And then you get some weirder shapes like octahedral and trigonal, pyramid, bipyramidal. But I guess just you should understand the concept first and then memorize it, which is that when you have electrons that are surrounding an atom, those electrons want to get as far away from each other as possible because remember, they're all negatively charged. And so they're going to create some sort of geometry. And so this is kind of the definition of what geometry they're making. The hybridization refers to the atomic orbitals that are being created by the bond. Right? So let's say that I have H2O, right? Let's use white, okay? Let's say I have H2O. So what is the shape of this, right? Let's look at the shape of it. H2O is probably a little difficult. Let's start with carbon dioxide. Carbon dioxide formula structure. Okay, so I'm just going to show you this. So carbon dioxide has a linear shape, right? These electrons on carbon want to get as far away from each other as possible. And there's no lone pairs here. All the electrons are in bonds on the carbon. And so it's going to have a linear shape because we essentially have 2 spaces. And so those spaces want to get as far away from each other as possible. And so this is an sp structure, okay? Let's say that I have an sp2, or let's start with sp3. So what would be an sp3? Let's say NH3 structure. Okay, so this has an sp3, a trigonal pyramidal, and you can see that this NH3 has 1, 2, 3 bonds and 1 lone pair. And so this lone pair is going to take up a little bit more space, and these bonds are also going to take up space. So it's going to kind of be like a tetrahedral shape, but since there's a lone pair, it's going to be trigonal pyramidal, right? So it's going to be trigonal pyramidal, right? So you can kind of see there's 3 bonded pairs and 1 lone pair. So the geometry is going to be tetrahedral, and it's going to be, the shape is going to be trigonal pyramidal. You can figure out what the bond angles here are by looking at what sort of hybridization does it have. And so you can kind of just figure out how many electron groups are around the central atom, how many of those are bonded pairs. Bonded pairs means how many bonds are there, and how many lone pairs are there. And then you can figure out what the shape is, and then you can figure out what the angle is for that geometry. Okay. Good. I guess the last thing I want to mention is hybridization, which is a very confusing concept. And let's just, for me at least, maybe it'll take you like a second to understand. But hybridization is kind of like, let's see if I can get a good image. Hybridization kind of refers to the bonds that are being formed between atoms, right? And so, let's see. Okay, so let's say here we can figure out what type of hybridization there is based on how many attached atoms there are, right? Or how many lone pairs there are. And so you can figure out that something like oxygen here has sp2 because it has 1 bond to the hydrogen, 1 bond over here, and then it should have So you can figure out what the hybridization is by looking at how many things are surrounding it. So here you see 2 lone pairs and 2 attached atoms, so that's sp3 because there's 4. You can look at 2 different groups, that's 4. You can look at 1 lone pair, 1 bond, and then 2 bonds here. So there's 3 attached atoms and 1 lone pair, so 4. These are all sp3 hybridized. Okay. Whew. Okay, here this is actually a pretty simple one, which is compounds and stoichiometry. So the most important thing here is kind of molarity and maybe equivalence. Sorry, I'm using white. Molarity and maybe equivalence, right? And so you just want to know basically molarity is the number of moles of whatever you're looking at over the liters of the solvent, and the equivalence is kind of how many equivalents of H plus or H plus or OH minus are you forming here? Okay, the naming ions is kind of important. You want to know that if you're looking at iron 2, then it's ferrous, and if you're looking at iron 3, then it's ferric. This refers to the ion, the cation, right? So if it's Cu plus, then it's cuprous, and if it's Cu2 plus, then it's cupric. So basically, the thing to remember is that it's us or ic, depending on the lesser or greater charge, right? The other thing to know is that when you have an anion, you remove the ending and you add an ide. So this is hydride, fluoride, oxide, sulfide, nitride, phosphide, right? The next thing is oxyanions. Oxyanions are polyatomic anions that contain oxygen. So more oxygen is an 8 and less oxygen is an ite. So the best example of this is nitrate and nitrite. Fewer oxygens, that's nitrite. More oxygens, that's nitrate. More oxygens, that's sulfate. Fewer oxygens, that's sulfite. The next one is prefixes, right? So this is hypochlorite, and this is chlorite, and this is chlorate, this is perchlorate, right? So that's kind of a fun example too. So there's only 1 oxygen, here there's 4 oxygens, so here hypochlorite, chlorite, chlorate, and perchlorate. The next one is how many hydrogens are bonded to it, right? So here you have H2PO4 minus, which is dihydrogen phosphate. Here it's hydrogen sulfate. A term that we use for this is bisulfate, right? But this is hydrogen sulfate. This is hydrogen carbonate, but a term that a lot of chemists use is bicarbonate. Okay. And the next thing that you kind of have to remember is I guess one thing you want to remember is then you're looking at an acid that ic is when you have more oxygens and us is when you have fewer oxygens. And us, again, is when you have fewer oxygens, right? So if I'm looking at HCl, or sorry, let's say oxygen acids. Okay. So if I'm looking at the acid version of this, right, then it's an oxyacid. And the anion name, this one, is hypochlorite. But if I was looking at the acid version, then it would be hypochlorous acid. Okay? Chlorous acid, chloric acid, and perchloric acid. Makes sense? Okay? The next thing to know is the type of reaction that we're looking at. And so combination is when you combine two things. Decomposition is when you break down something. Combustion is when you add a hydrocarbon, which means it's only made up of carbon and hydrogens, with an oxygen, and you get carbon dioxide and water. Okay, and that's a pretty common equation that you can see whenever we're combusting something. Single displacement is when we have a compound like AgNO3, and we replace the Ag with Cu, right? So that's single displacement. Double displacement is when we just swap around these. So calcium chloride and silver nitrate, you kind of switch up the calcium and that silver. Okay, the next thing is neutralization, which is when you have an acid, hydrochloric acid, and base, sodium hydroxide. You add them and you get a salt, NaCl, and water, H2O. That's called a neutralization reaction. You had an acid and base, and you just result with a salt and a water. Whew.
Okay, now we're on chemical kinetics. And here it's pretty important that you know these equations in the order. So we have 0th order, 1st order, and 2nd order. And essentially what this means is that does the rate of the reaction depend on the substrate? And if so, how much does the substrate actually affect the rate? And so in a 0 order, it doesn't affect it at all. In a 1st order, it does affect it linearly. And in 2nd order, the rate is affected by the square of the substrate. And so I always used to have trouble memorizing these equations until what I actually did was start memorizing these graphs. And then if you kind of remember these graphs, because they're visual, it's a lot easier to remember them. And then you can derive these equations from those graphs. So that's what I'll tell you over here. So if you remember that this is A on the y-axis and this is time, and you remember that this is downward going, and you remember that for all of these, the slope is always k or negative k. So the slope here is negative k, which means that we know that the mx plus b, we know that the mx is going to be negative kt, where negative k is the m, and then t is the x, plus b. B is where it hits the y-axis, which is a naught. And that's going to equal the y, which is a. And so that's how we get this equation. So you can actually derive this equation if you just remember what this graph looks like. Now, you can also derive the half-lives of each of these by just remembering these graphs, because you can think, okay, if I plug in where does a equal half of a naught, then you subtract this on both sides. You get negative 1/2 of a equals negative kt. You get kt equals 1/2 at, and then you get the half-life is equal to a naught over 2k. And I would recommend you just working that out by hand. It'll make sense. Okay, the next one is, this one is a little bit more complicated, 1st order. So just remember that the substrate affects this rate linearly. And if you just remember this graph again, you'll be able to derive this. It's just a little bit more difficult. So let's say we take the ln of both sides, the natural log of both sides. What we get, if you remember logarithmic rules, we get the ln of this plus the ln of this, because that's how you do the natural log of two things multiplied, is you're allowed to separate them if you add the natural logs of them. So you get ln of a equals ln of a naught plus the ln of e to the power of negative kt. So the natural log of e to the power of negative kt is just negative kt, which fortunately for us is we get from the slope, because this is the slope here is negative k, plus the natural log of a naught, which is actually where this where this y-intercept is of this line. It's the natural log of a naught, and that's equal to the natural log of a. So I'd recommend you just take the natural log of this equation and try to derive it by hand, and it'll make sense to you how you can take that from this graph. Then third graph is a second order reaction. Unfortunately, this is a little bit easier. So in this equation, you can see this thing. We know the slope is positive k, so it's positive kt plus the y-intercept here would be 1 over a naught. So 1 over a naught plus kt equals 1 over a, which is our y. So that's kind of how you can derive this. So again, what you really have to memorize is that this graph points downward, this graph points downward, this graph points upward. So you can figure out if it's negative k or positive k. And then the second thing you would have to memorize is these y. What do these y's represent? If you can remember that, then you can derive, basically you can derive all of this, which is pretty amazing. If you just remember, like, this goes down, this goes down, this goes up, and you remember that this is 1 over a, this is natural log of a, this is a. And then finally you have the rate, units of rate constant. This should make sense to you if you just kind of plug it in for k. So the rate is moles over seconds, which makes sense. And then for here, you have rate equals k times something. So this already has the unit molar, right? So you know that the rate has to be molar over second. So you just do k is 1 over second. So now you get molar over second. And then finally, you know here that this is molar squared. So if you do 1 over molar second, then you get molar over second. So again, you can just try that by hand and it'll make sense why these units are true. So again, if you just remember this, you can derive everything over here, and it's a lot simpler. Okay, the next thing to mention is that these over here, this is a lot closer to like a straight line. So it's a lot closer to a first order kinetics equation. And then over here, this is a lot closer to a zero order kinetics reaction, because as you add more substrate, it doesn't really change the rate over here. As you add more substrate over here, it's almost kind of like a straight line where it's going upward. So that's what this is saying over here. And remember, this is called the Michaelis-Menten curve. This is kind of how those two scientists describe the rate of enzymes reacting with substrates. Okay, next you have types of reactions. So over here, this is pretty high yield too. So combination is when you combine two things. Decomposition is when a single thing breaks down. Combustion is when you add a hydrocarbon and oxygen and you get carbon dioxide and water. Single displacement is when you take like a atom and you add it to a compound, and then your ions switch places. And then you have double displacement, which is kind of the same thing as single displacement, but it's happening with both compounds. So you're switching them around. So you get this calcium is now bonded to this nitrate, and this silver is now bonded to this chloride. Now you have neutralization. Neutralization is a type of double replacement reaction. So this is when you take an acid and a base and you make a salt and water. So HCl plus sodium hydroxide makes sodium chloride plus water. And then you have hydrolysis. And hydrolysis is when you take water and you break down a bond. Okay, next we have Gibbs free energy. So Gibbs free energy is kind of telling you, does the universe want this reaction to happen or not? If Gibbs free energy is negative, then it's exergonic, the universe wants it to happen, and if it's positive, then it's endergonic. The universe doesn't naturally spontaneously move in that direction. You calculate Gibbs free energy based on the heat that the reaction makes, and you also calculate it based on the entropy that the reaction makes. And so if the reaction increases entropy and also releases heat, then the universe wants that to happen. And that's kind of how Gibbs free energy is calculated. You should know the equation for Gibbs free energy, but we'll get to that later. Okay, next is the Arrhenius equation. So Arrhenius equation is K equals A times E to the power of negative EA over RT. This is a very important equation. And here we also get definition of rate. So if you have these four compounds that are reacting, then the rate is equal to how fast do we get rid of this compound. It's also equal to how fast do we get rid of this compound. It's also equal to how fast do we make this compound. And it's also equal to how fast we make this compound. Now you have to take into the fact that there's these coefficients as well. So you have to divide it by the coefficients. Because let's say here it's 5C plus 1D. Then we're supposed to make 5 times more of C as compared to D. And so that's why we divide by these coefficients. Now we have the rate law. In the rate law, you just take the substrates, so this A and the B, and you do it to the power of some value, x and y, and you multiply it by a rate constant, and that's how you get the rate of the reaction. And it's also important to know that these are not just the coefficients of the reaction. These are things that you can only find by actually doing the experiment and figuring out like, oh, how fast, how much do A and B manipulate the equation. So sometimes in the MCAT, they'll actually give you lab values and they'll tell you like, oh, when A goes from 1 to 4, this reaction doubled. And so now you should be able to say like, oh, what is the exponent for A? And when B went from 1 to 2, this reaction 8x'd. So now you should be able to tell me like, what's the exponent for B? Now we have radioactive decay, and I went through this in the physics section as well, but radioactive decay is just telling you how fast does some of the radioactive elements decompose. And so this is the equation that describes that. Also very high yield, you should know this equation. Okay, next we have reaction mechanism. So you have multiple steps in a reaction. Even though the reaction might just be one thing, there's actually multiple steps that are going on in that reaction. And one of those steps is a rate determining step. That's the slowest step, and basically everything else is dependent on how fast or how slow does that rate limiting step go. We call the middle compounds intermediates because those don't actually show up in our final equation. Those are things that we produce in the middle in step 1, and then in step 2 we get rid of it, and so that's why those are called intermediates. But it is really, really high yield to know what a rate determining step is. It's just the slowest step. Okay, now we have Arrhenius equation, also very high yield. It's more high yield to know the relationships here than to actually know the equation itself. So I talked about Arrhenius equation. This is the rate over here, the rate constant, and this is basically how do we determine what the rate constant of an equation is. So it's equal to this thing called the frequency factor, which is going to be given to you, times E to the power of negative EA, that's the activation energy in the reaction, divided by the gas constant times the temperature in Kelvin. So it's also important to know that this T over here is represented in Kelvin, and you want to make the conversion before you do anything. So remember, add 273 to the Celsius. Okay, it's important to know the trends here. So as you increase the frequency factor, A, you're going to get a higher rate constant. As you increase the T, well, we have to reason this out. So T goes up, which means that this thing, let's forget about the negative sign for now. That means this fraction, if T goes up, this fraction is going down. But now we have to factor in the negative sign. So now we know that this fraction is going up, right? Now e to the power of a fraction that's increased is increased, and so that's why the k is higher. Work this out by hand because it'll make a lot more sense. But that means that when t is increasing, so is k. And so that kind of logically makes sense too. If you have like all these atoms that need to react with each other, if it's really cold and there's not much if the temperature is really small, these compounds are not going to move that quickly and bump into each other. But when the temperature is really, really high, these compounds are all going to hit each other, and so we're going to have a higher rate constant. So that's what that's saying. Okay, now we have equilibrium constant. So this is the same equation that we were looking at before. We can represent the equilibrium constant by just taking C and D and adding coefficients to it by exponents, and then we divide it by A and B, and again we take the coefficients and make those exponents, and that's called the equilibrium constant. By figuring out what this is, what this value is, basically what you're doing is you're taking the molar of the substrates here of these compounds. So let's say I told you, oh, I have 5 molar of this, and I have like 2 molar of this, and I have 1 molar of this, and I have 3 molars of this. That's going to tell you like the KEQ, what is the equilibrium constant here. Now we also have the reaction quotient, which is QC. And over here it's important to know that QC is actually like how much of everything do you actually have. So if I have 5, 4, 1, 2, right? Those are the values I put into QC. KEQ is like telling you what is the normal equilibrium constant for that reaction. And I recommend you just do like a question from UWorld or some free online resource about reaction quotients and equilibrium constants, because it'll make a lot more sense when you actually do a question, and you'll understand like, oh, if the like what I'll get into here, it'll basically tell you which direction does the reaction go. So when I talk about this equation over here, I want to figure out, like, is this equation more likely to go this way, or is it more likely to go this way? Because this equation can go in either direction, and it actually depends on how much of these compounds do I have. And so when you have a lot of A, it's more likely to push this equation this way, and when I have a lot of D, it's more likely to push this equation this way. And so that is what informs the QC value. And so if my QC is smaller than the KEQ, then this reaction again is going to go this way. If my KEQ is equal to Q, that means that this reaction is in equilibrium. It means that delta G, the Gibbs free energy, is 0, and so the equation is not going to go one way or the other. It's just going to stay there. And then if Q is greater than KEQ, then that means there's a lot more of this than there is of this, and so the equation is going to go this way. So again, just do a practice example of this and it'll make more sense. Usually how it'll show up is they tell you what is the amount of each of these do you actually have, and then it'll tell you, oh, the normal KEQ of this reaction is like 5, and you have to calculate the QC, and the QC will be like 1 or something, and you know 1 is less than 5, so you know the equation based on this is going to go this way. All right, now we have kinetic and thermodynamic control. So kinetic products versus thermodynamic products. I'm going to show you an example because it'll be easier. Okay, so this is the difference between, so this is a thermodynamic product over here, because the activation energy is a lot higher, so it takes a lot more energy to go over and actually make this end product E. But this E end product is a lot more stable than D over here. So this is a thermodynamic product. The Gibbs free energy is a lot greater. It just takes a lot more energy to actually get there. Now, kinetic product is just what you would get to without as much activation energy. And so you don't get as much of a stable product at the end, but it's a lot easier, meaning it takes a lot less activation energy to get there. So that's the difference. Okay, so that's kinetic, higher in free energy. These are the products that can form at lower temperatures. They're fast, in quotes, because they can form more quickly under such conditions. These thermodynamic products are slower but more spontaneous, meaning more negative delta G, and that's important. It's more spontaneous. The universe wants to make that more. Okay. Le Chatelier's principle: if stress is applied to a system, the system shifts to relieve that stress. So remember when I was saying, like, if you have a lot of the products, then you'll shift toward the substrate, and if you have a lot of the substrate, you'll shift toward the product. That's basically the Chatelier's principle. Now, this is a good question that they might use to apply multiple different principles, which is, let's say this is happening in the body. This is a reaction. This is actually something that's going to come up in med school a lot, which is, okay, this person has this bicarbonate buffer in their system. Let's say now we give them a medicine that's going to increase the pH in their gut or something, right? So what's going to happen is, if we increase the pH, that means we're decreasing the H+, which means it's going to go because we're decreasing the H+, we want to make more of it. So that's why the equation is going to go towards the right. And so that means essentially that we're going to have less respiration because we're going more this way. So that's why this is less respiration. Because we have less respiration, we're not going to breathe as much, and we're going to have more trapped CO2. Now over here, it's less pH, which means higher H+, and that means that we're going to go this way, which means we're going to produce more carbon dioxide, which means we're going to respirate more and blow off that CO2. So that's basically Le Chatelier's principle. Okay, next we have systems and processes, and this is thermochemistry. So systems and processes, we have isolated system, closed system, open system, isothermal, adiabatic. I used to always be confused with these until I kind of simplified it for myself. So let's say this is a system, right? If it's isolated, that means nothing is getting in or out, and there's no heat exchange, and there's no there's no matter exchange. If it's a closed system, that's more like a normal system where there can be heat escape or heat entering, but there's no matter that's leaving, like no physical elements are leaving. Then we have an open system. And open systems is like, I think of it like an open fence, like matter can leave and so can energy. So anything can come in or out. That's open system. Now, isothermal processes is when you have a constant temperature. So let's say like there's this gas with a piston in it, right? let's say the gas is expanding, right? Usually when the gas is expanding, it's doing work, and so there might be heat that's leaving, right? But you might have like temperature that's constantly heating this up, and so that's an isothermal process because there's constant temperature in here, even though there's a heat exchange happening. Adiabatic means there's no heat exchange happening, but the temperature of this might change. There's just no heat exchange, so this might be getting cooler as it's doing work and releasing heat. But sorry, let me repeat myself. So adiabatic means there's no heat exchange with the environment. So you can imagine like this is so thick walls that there's no heat exchange, and so this is the same heat at the same time. The temperature might be changing, but the heat is the same. Now we have isobaric and isovolumetric. Isobaric means there's constant pressure. Isovolumetric means constant volume. Now, let's talk about state and state functions. So state functions represents the equilibrium state. These are pathway independent. So this is like pressure, density, temperature, volume, enthalpy, internal energy, Gibbs free energy, entropy. These are just physical properties of our equilibrium, right? It's not gonna change any, like the path is not going to change anything about our equilibrium values. This Gibbs free energy of reaction is going to stay the same whether or not we have different amounts of the substrate or the product. The internal energy is not going to change, the pressure is not going to change. Those are things. Okay, standard conditions. This is kind of important because they might give you reactions happening in standard conditions. So just remember, this is 298, 1 atmosphere, and then 1 molar. Those are standard conditions for gases. Okay, and then we have fusion, freezing, vaporization, sublimation, deposition. So fusion is a solid going to liquid, freezing is liquid to solid, vaporization is liquid to gas, sublimation is solid to gas, and then deposition is gas to solid. Just remember all of these are important. And then triple point is this unique point where all three of those states can coexist. So you can have, at that point of temperature and pressure, you can have a solid, liquid, or gas. You can also have a supercritical fluid, which is kind of like in this space where the density of the gas is equal to the density of liquid, and there's no distinction between those two phases. All right, now we have Gibbs free energy, and this is what I was talking about before. So we have the enthalpy and the entropy, and those are what determines Gibbs free energy. So just remember that this is the equation, and they might give you these values, and you'll have to figure out, oh, is Gibbs free energy negative or positive? And it's important to know that reactions that have negative Gibbs free energy are spontaneous. This is kind of a chart to help you out with this equation. Okay, next we have temperature and heat. So temperature is the measure of the average kinetic energy of a substance. So you can imagine like this is a box and these are all the particles, and if they're moving around really quickly, that means that there's a high temperature. If they're moving around really slowly, then that's a low temperature, and that's kind of how you can measure what temperature is. This is just helpful points to remember. So I try to remember body temperature is 37 degrees or 98.6, and I also remember 0 degrees or 32 degrees is freezing. This is the equation, not too high yield that you know this equation. Okay, heat is just the transfer of energy that results from differences in temperature. So if you have a hot cup of coffee on a cold day, then there's going to be heat exchange because this has a higher temperature than the surroundings. Okay, now we have enthalpy. So enthalpy is the measure of potential energy of a system found in intermolecular attractions and chemical bonds. You can imagine that if there's a lot of chemical bonds that are causing higher enthalpy, then maybe that might result in, like, if this is a very unstable bond between these two things, then there might be a desire to break that bond and release a lot of energy. Phase changes, so solid to liquid to gas, that's endothermic, that requires heat, right? If you have an ice cube, it's only going to melt if there's a hot sun outside. So that's what that's saying basically. And then gas to liquid to solid is exothermic, it releases heat. So when a gas goes into liquid and then a liquid goes into solid, that's releasing heat. Hess's law is that enthalpy changes are additive, and you're probably going to be tested on this. I would do just a question on Hess's law, and it's going to make a lot more sense. But basically, you just take the the reaction, the heat of formation for that reaction, and that's going to equal the heat that it took to make those products minus the heat that the reactants. You can also do this using bond dissociation energies, and so in this one it's reverse, and that's because you're actually disassociating the reactants rather than the products, and so that's why you do the reverse over here, because yeah, that's basically how it works. So heat of formation and heat and the bond dissociation, these are kind of like opposites, right? So that's why you flip the equations around. Now you have entropy. Entropy is just the disorderedness of that system, and it's equal to Q divided by T. Just remember this is an important equation. And just know that the standard entropy of reaction is the entropy change that it took to make the products minus the entropy change that it took to make the reactants. Okay, now we have Gibbs free energy, and this is the same equation I talked about before. Again, it's just the products minus the reactants, and we can figure it out actually from just the KEQ, the equilibrium constant. The equilibrium constant is just what are the concentrations at equilibrium of the substrates in the products. And so you do this equation and you can figure out what is the free energy that's produced by this reaction. You can also do it by figuring out the Q, and basically that's going to tell you what is the free energy currently. And if the free energy at this point is less than 0, then that means that it's a spontaneous, it was spontaneous to reach that point. But if it's greater than 0, then it's non-spontaneous. And the difference between delta G and delta G prime always confused me. So this is the free energy at equilibrium. This is the free energy at the point that you are at. So it's kind of like the difference between Q and K. K is a representation of equilibrium. Q is just where you are based on the substrates and products that you have. Okay. Okay, next we're on gas phase, and here this is pretty high yield. So we have ideal gases and STP. STP is the standard condition. So if somebody says that you are at STP, that means you're at 0 degrees Celsius, 273 degrees Kelvin, and 1 atm. And at STP, 1 mole of gas is 22.4 liters. That's also pretty important for you to know. I'd say the most important thing here is the 1 atm is 760 mmHg. That'll save you a lot of time. And then it's also kind of helpful to know it's about 100 kilopascals or kPa. So that's pretty helpful too. Torr and mmHg is the same thing, or same like unit conversion. Ideal gases are just theoretical gases. When you have like this box and this gas, the molecules are bouncing around, usually these molecules actually take up space, and when they hit each other, there's some energy that's lost. But in ideal gases, you just consider that these particles are just super tiny and that there's no energy that's lost. These collisions are perfectly elastic. This happens usually when the temperature is really high, so these particles are moving around really quickly, and the pressure is very low. Next we have the ideal gas law. This is super high yield. Make sure you know this like the back of your hand. PV equals nRT. R is 8.314 joules per mole K. And then the density of gas is just the PM over RT. That's also very high yield to know. So if somebody gives you the molarity and the pressure and the volume, you can know the temperature. You should be able to figure out the density of that gas. This is the combined gas law. This is kind of the one that combines all three of these laws. And this law is that PV over T equals PV over T. And basically what you're doing is you're taking this equation and you just know that N is constant, and so you're able to derive this combined gas law. Boyle, Charles, and Gay-Lussac, they're people who figured out like the relationship between P, V, and T. And once they figured that out, you can combine those laws into the combined gas law. Okay, the last thing that the combined gas law does not include is the Avogadro's principle, which kind of takes the N part into it. So if you have N1 over V1, that's equal to N2 over V2. So these are, again, very important laws to know. You can figure out a lot about the pressure of a gas, the temperature of a gas, the volume of gas, the number of moles in the gas, just based on these equations, okay? So now we have Dalton's law, and Dalton's law is just that the total pressure, so if I have this box and there's like gas A and gas B and gas C, I can just add the pressure of these gases and I'll get the total pressure in that box. There's also Dalton's law, which is that I give you the total pressure, and then I tell you like, oh, the mole fraction of gas A is like 1 out of 5, then you can figure out the gas A is just 1/5 of the total pressure of the gases. Henry's law is this thing. The molarity of A is dependent on the pressure of A times this constant, and so that's kind of Henry's law. Again, all of these are pretty important to know. You'll probably get questions on this, but it's really easy to get this down if you just do 1 or 2 questions on gas laws, and you'll be able to solve all the questions that you get. Next is diatomic gases, so this is probably going to show up too. Just know that the HNFOICB, this is a really helpful mnemonic. I used to use this mnemonic all the time to remember all the ones that have that exist as diatomic particles. So you're not going to see just that. You're going to see always like, it's going to be like this. Or you're not going to see like O alone. You're going to see O2. So these are all usually exist as diatomic molecules. Okay, the next is real gases. Remember when I said ideal gases usually are under high temperature, low pressure? Well, real gases deviate from ideal behavior. Those particles actually do take up space, and they do lose energy when they hit each other, and that happens usually when there's low temperature and high pressure. Okay, so now this is a little bit less high yield and a little bit more complicated. I'll talk about van der Waals equation first. Again, it's not that important that you know it, but this minus NB basically accounts for the fact that these particles have volume, and so that's why we're subtracting from the volume of the gas. And then this accounts for the fact that there's attractive forces between these particles. And so when these particles are bouncing around and hitting each other, there's some attractive forces. And so there's a little bit more pressure than you would have in an ideal gas. And that's this is just basically a modified equation for PV equals nRT. Okay, now you have this. This is, again, not that high yield for you to know. If you have moderately elevated pressure, lower temperature, then the real gases are going to occupy less volume. The reason for that is because these particles have intermolecular attraction, and so they're going to be attracted to each other. And so this gas will take up less space than if it was an ideal gas. But at extremely low temperature and high pressure, what's going to happen is that these real gases will take up more volume because the particles themselves are actually taking up space. They're actually a lot bigger than in an ideal gas where you just assume that these particles take up negligible space. So that's again not that important that you remember, but it's helpful to understand why that's true. Okay, now we have kinetic molecular theory, and we've kind of already gone over this, but if you have this gas and these particles are all moving around, you can figure out what is the kinetic energy of a gas based on 1/2 mv squared. And you can also realize that based on this equation, you will realize that the kinetic energy of a gas is directly related to the temperature of that gas. So at higher temperatures, that means that kinetic energy is higher, which means that this velocity is higher. So these particles are moving faster. At greater molar masses, then the molecules are moving slower. And that makes sense. They're heavier, so they're going to be slower than if they were lighter. Okay, this is also important. This is root mean squared. I want you to remember this equation. Basically, it's square root of 3RT over molarity. And the important thing is that you just understand this relationship. So here we know that the speed is kind of directly related to the temperature, which we just talked about, and inversely related to the molarity, which is kind of similar to the heaviness of that particle. Diffusion is that the spreading out of particles. So you can imagine if you have like really dense particles after you spray a Febreze bottle, it's going to diffuse through the air to all the places that are less full of that particle. And effusion is the movement of gas from one opening to another opening. So this is like an example of effusion. So effusion is these gases that are in this box are just going across to this side. That's effusion. And it's usually through a smaller opening, so it has to be through a smaller opening. That's effusion. Okay, now we have Graham's law. Graham's law is basically that R1 over R2 is inversely proportional to the square root of M2 over M1. So basically what that's saying is that the greater the molar mass, the slower the diffusion or effusion. That again makes sense. If this gas is just heavier, then it's going to go slower. But if this gas is lighter, then it's going to go quicker. the diffusion and effusion is going to be faster. So that's what Graham's law is. Again, it's really important that you understand these equations, but it's more important that you understand the relationship between the variables than the actual equations themselves. The equations are important. They might ask you like, oh, what is the value? But they're more likely to ask you, based on these two molarities, what's the relationship between these two gases? Okay, these are the 7 diatomic gases. Now we're on solutions. So solutions, the terminology, solution is a homogeneous mixture. So there's basically this mixture, and there's solvent particles, and solvent particles is kind of like water is a really popular solvent, and those surround solute particles, and they're surrounded by electrostatic interactions. So you can imagine like a solution of NaCl in water, and the water, the H2O molecules have electrostatic interactions because of this dipole that hydrogen and oxygen form, and those have electrostatic interactions with the NaCl. Now we have solvation or dissolution, and that's basically when this solute dissolves in the solvent. So you can imagine salt dissolving in water, and what's happening is that the Na plus is splitting up with the Cl minus into ions. And it's important to know that most dissolutions are endothermic, but the dissolution of gas into liquid is exothermic. It's probably not going to show up too much, but it's just kind of important to understand why that's true. Now we have solubility. Solubility is just the maximum amount of solute that you can dissolve in a solvent in a given temperature. You can imagine that if you have a cup of water, you can add salt to it and it's going to dissolve, but there can be you can add such an excessive amount of salt that eventually you won't be able to dissolve that salt anymore. And that's what solubility is referring to. Molar solubility is just the molarity of solute at saturation. Saturation is basically like you keep adding salt until you can't add any more salt, because otherwise it's going to precipitate. You have complex ions. Complex ions is a cation bonded to at least one ligand in which there's electron pair donor. And I'll show you an example of complex ions. So this is an example of a complex ion over here. You can see that there's a copper, and then there's all these H2O particles that are ligands of this copper particle, and those are basically, that's a complex ion. So solubility in water is something I just talked about. Now we're on concentration. Concentration is, you can imagine, percent by mass. So this is all really important, just definitions that you should know. So the mass solute over the mass solution times 100%, that's the percent by mass concentration. We have the mole fraction. Mole fraction is just the moles of the solute over the total number of moles. We have molarity. Molarity is moles of solute over liters of solution. So if I told you there's 1 mole of NaCl in 1 liter of water, that's 1 molar. And then there's molality. That's moles of solvent, moles of solute over kilograms of solvent. So it's, I guess one thing that I should have mentioned here is that I mistakenly said 1 liter of water. I should have said 1 liter of solution, because this denominator is referring to the solution, which is both of those combined, the NaCl and the water. This is kilograms of solvent, which is just the kilograms of the water. So that should make sense. And then we have normality. Normality is the number of equivalents divided by the liters of solution. A good example, I was always confused about normality, but you can imagine H3PO4. So there's multiple equivalents here because the number of H plus units that are being formed is actually 3 times, and so that's what that's referring to, number of equivalents. Okay, now we have dilutions, and so this is a really important concept, and you're definitely going to be asked about this, and it's a pretty simple equation, but it's kind of hard to understand when to apply it. So basically, if I told you I have 1 mole of NaCl solution, or sorry, 1 mole of NaCl in 1 liter of solution, basically that means that there's 1 molar, right, in 1 liter solution. Now let's say I want to dilute this so that it's actually 0.5 molar. How much water do I need to make this 1 molar solution into 0.5 molar? Well, that's when I just use this equation. So I know that this value is 1. I know this value is also 1. I know this value is 0.5. So what is the volume of solution I need? And then you can just figure out, oh, okay, this is actually 2. So I need to get an extra liter of solution to make this more dilute. Okay, now we have solutions equilibria. So This is solubility product constant. So this is KSP. KSP is basically kind of like the same concept as KEQ. This is telling us more about like what is the equilibrium constant for this dissolution equation. And so you're going to have an ion product. Ion product is basically the same thing as Q, and KSP is the same thing as K. And you'll see that if IP is ion product is something that describes where is the solution right now, and KSP is describing where is the solution at equilibrium. And so if IP is less than KSP, that means that this solution can actually handle more solute. If IP is equal to KSP, that means that the solution is saturated. And if IP is greater than KSP, that means that there's going to be a precipitate. Precipitate is like there's solid coming out of the solution because it can't handle any more of the solute. So you might see like sodium chloride crystal in a solution of supersaturated water, NaCl solution, just because this is supersaturated. And so that's what these are telling you. Okay, now we have formation or stability constant. This is just Kf, and that's basically the equilibrium constant for complex formation. Usually it's much greater than KSP. We have the common ion effect, and common ion effect is just describing that there's lower solubility of a compound in solution when it already contains one of those solutions in the compound. So an example of this would be like, let's say this is my solution, and I have like a calcium chloride that's already been dissolved, so there's already a lot of chloride ions in this solution, right? And now I'm trying to dissolve NaCl in the solution. Well, because I'm trying to dissolve NaCl in the solution, it already has a lot of chloride ions, so there's going to be the common ion effect, and so there's going to be a lot less sodium chloride that's able to dissolve just because there's already a lot of chloride in that solution. Now we have chelation, and chelation is something that they use in industrial chemistry where they'll try to sequester toxic metals from water by just adding a central cation, like what I was showing you before. Like let's say they add copper, and now all these things will be ligands to that copper. Or they'll use like these ligands, and they'll try to precipitate out this toxic metal. Okay, now we're on solubility rules. These I would just try to memorize, and I think if you haven't memorized them from chemistry class already, I think the best way to memorize it is to kind of look at the periodic table and be able to memorize it from there. So sodium, potassium, ammonia, these are always soluble. This nitrate is always soluble. Chloride, bromide, iodine is always soluble except when they're with these three compounds. This is soluble except when it's with this. So just kind of look at the periodic table and be able to say like, okay, this is soluble, this is soluble, this is soluble except when it's with this. And I'll let you try to memorize these. This is just, again, really high yield, and I'm sure you were tested on this in chemistry class as well, so just try your best to memorize all of this. Okay, now we have colligative properties. So this is kind of a little bit more about boiling point elevation, freezing point depression, osmolarity, osmotic pressure. So colligative properties is just the physical properties of solution, and it depends on the dissolved particles. And so the important thing is that it doesn't really matter about the chemical identity, which dissolved particle it is. Like, is it a lot of protons? Is it a lot of like chloride ions? It doesn't matter about that. More it matters about the concentration of those dissolved particles. So you have vapor pressure depression, you have boiling point elevation, and then you have freezing point depression. So basically what these are referring to is that if I have a cup of water, the freezing point is 0, boiling point is 100, right, for Celsius. But then if I add some particles to it, now the freezing point might be like -3, and the boiling point might be like 104. And these two equations, you can read them. Those are the equations that describe like what is the change in the freezing point and what is the change in the boiling point. And that's the way that you can figure out. So I try to always remember that solutes are going to increase the range of my freezing and boiling points. It's going to make the boiling point higher, and it's going to make the freezing point lower. Then we have Raoult's law, and that's vapor pressure depression. And so that's basically saying the presence of other solutes will decrease the evaporation rate of the solvent. And so that means that there's a decrease in the pressure for vaporization. So that's also an important thing to know. Whew. All right, now we have osmolarity. Osmolarity is just the number of individual particles in the solution. So because NaCl dissolves completely, 1 molar of NaCl is 2 osmoles per liter, because the NaCl splits up into Na and Cl, and so that's one osm and that's another osm. Okay, now we have osmotic pressure, and this is the sucking pressure that's generated by solutions in which water is drawn into the solution. And this is not like a super high yield thing for you to memorize, but it is important for you to know the relationship. So this is osmotic pressure, this is the molarity, and then this is the temperature, and this is gas constant, and this is just a constant Van 't Hoff factor. So that's the osmotic pressure, that's the sucking pressure generated by solutions in which water is drawn into the solution. Something we learned in med school is that there's this thing called osmotic diarrhea, which is that there's this basically it's watery diarrhea caused by this osmotic pressure. Okay, now let's talk about acids and bases. So we have Arrhenius acid, Arrhenius base, Bronsted-Lowry acid, Bronsted-Lowry base. So Arrhenius acid basically makes H+. This is the original definition of acids. And then Arrhenius bases produce OH-. Then they decided that they need to expand the definition a little bit. And so they said Bronsted-Lowry acids, they donate H+, versus Bronsted-Lowry bases accept H+. And then finally we had Lewis acids and Lewis bases. And that's just basically about electrons. Lewis acids accept electrons, Lewis bases donate electrons, and so it's kind of the opposite donation and accepting relationship here, but this is what Lewis acids and Lewis bases describe. These are all technically definitions of acids and bases. It just depends on how you define an acid or a base. Okay, and then it's also important to know that like Arrhenius base might describe a compound that's not necessarily a Lewis base. And Bronsted-Lowry base might be different from a Lewis base. So these compounds might not be the exact same. They're similar, but sometimes there's exceptions to their overlap. Okay, now there's amphoteric species. So that means that something can be both an acid or a base. And then we have polyperiodic acids, which means that there's multiple H atoms. So like H3PO4, you have multiple protons that can leave this. And so that's a polyperiodic acid. Okay, now we have the water dissociation constant. Really memorize this, 10 to the negative 14. That's very important. And then remember that Ka times Kb is 10 to the negative 14 is Kw. All right, pH, pOH, you have to know this. Or you should know this by your exam, that pH is negative log H plus, pOH is negative log OH minus, and then pH plus pOH is equal to 14. Make sure you remember this as a really high yield. H plus is 10 to the negative pH, 10 to the power of negative pH. Okay, this is kind of helpful. P value you can approximate as the negative B over here plus 0.A. And if you do, 10 to the power, you'll kind of understand the reasoning behind that. Okay, there's strong acids and strong bases, and then weak acids and weak bases. It's very important to know the difference here. Strong acid, if I put it in water, like H2SO4, right? If I put this in water, it's immediately going to dissociate into the H plus the HSO4 minus, versus like a weaker, or like HCl, right? HCl is immediately going to dissociate. You won't see any of HCl in water. It'll always dissociate immediately. Weak acids and weak bases don't completely dissociate, so there's still some of that compound left over. There's acid dissociation and base dissociation constant, and this basically is you take the H3O plus in the solution, you take the A minus in the solution, you multiply them, and then divide it by HA. That's Ka. And you can do something similar for Kb. And then you can figure out pKa and pKb, and that's basically telling you how strong is the acid or how strong is the base. These are all measures of how strong is your acid or base based on how much dissociation happens. So you can imagine if there's so much dissociation, then this numerator will be high and this will be a strong acid. If there's so much dissociation here, there's going to be a very strong base. And then pKa plus pKb equals pKw, which is equal to 14. This is like basically the same equation as this right here. Okay, now we have conjugate acids, conjugate bases. So if you have a strong acid, you have a weak conjugate. That should make sense, because basically for you to go from HCl that produces H plus Cl minus. Now for H plus and Cl minus to form HCl, that's like for Cl minus to pair up with an H plus and form HCl, that's like basically impossible. So that's why it's a very weak conjugate. We wouldn't even call it a base at that point. So that's that. And then we have neutralization reactions. Neutralization reactions form salt and then sometimes H2O. Okay, now we have buffers. Buffers are very important physiologically. It's basically we take a weak acid or a weak base and its conjugate salt, and it resists the changes in pH. So it's really important in your body to have buffers, like the HCO3 system. This is a weak acid, right? And so it helps to buffer and resist changes in pH. Okay, now we have HCO3 is a weak base, I should mention, because you can form H2CO3, and this is kind of the equation that happens. Okay, now we have Henderson-Hasselbalch equation. Make sure you memorize this. This is very important. pH equals pKa plus log base over acid, and then this is kind of the opposite. POH equals pKb plus log base over acid. And this is, again, really, really high yield for you to remember, because basically you can figure out what is the relationship between pH and pKa based on this ratio. Okay. Okay, and then the other thing to mention, this is kind of helpful, is that when the base over acid is equal, so it's at the half equivalence point, then this becomes 1, which means log of 1 is 0, which means that the pH is equal to the pKa. So if you're looking at a titration curve, and I'm skipping a little bit, but if you look at the point at which there's half equivalence point, you can actually figure out what is the pH of that solution. So if I'm working with like some base or acid that I'm not, so this is a base actually, so if I'm not actually sure what is this base, I can figure out what the pH of this is by just looking at the half equivalence point, and that's over here, and then I can figure out, oh, well, the pH is about 10.9 over here, so that means that the pKa is 9, and I can actually figure out like what base is this based on that. Okay, now we have polyvalence and normality. So we've kind of already gone over that. Equivalence is 1 mole of the species of interest. Normality is the number of equivalents in a solution. And so if I took H3PO4, there's 6 equivalents or 6 normality of this, because there's 1 mole of this creates 3 moles of H plus, so 2 molar of this is 6 normality. Okay, now we have polyvalent. Polyvalent means that it accepts multiple equivalents or donates multiple equivalents. So this is a polyvalent acid like we talked before. All right, now we have titrations. So titrations is something you've talked about in chemistry lab already. You have half equivalence point, which is what I just mentioned. You also have equivalence point. Equivalence point is the point at which there's equal amounts of acid and base. So this is the equivalence point over here. It's a very important point for you to know, and it's basically halfway through the downward trajectory of that. Okay, now we have pH at equivalence point. So pH at equivalence point, if it's a strong acid that you're titrating with a strong base, then pH is going to be 7. And then the others you can kind of reason through. If it's a weak acid that you're titrating with a strong base, well, then pH is going to be greater than 7. If it's a weak base, strong acid, pH will be less than 7. So you can kind of reason through that. Indicators help you figure out, well, where should the indicators are basically things that change color close to a place where you expect the pH to change. And so if the color suddenly changes at like pH 7, then I know like, oh, we're at pH 7, and it just helps us kind of look at the titration itself. These are tests that you can use, not too important that you remember all of these, but like the litmus test, acid are red, base is blue, neutral is purple. Again, not too important that you know this. Endpoint is when the indicator reaches full color. So basically endpoint is going to be, if we chose our indicator properly, endpoint should be somewhere close to the equivalence point. Okay, and then we have polyvalent acid-base titrations, and so in polyvalent acid-base titrations, there's going to be multiple points at which you can find equivalence points. Okay, so this is basically what a titration looks like, and I'm not going to go too much into it because this is probably something that you've looked at in chemistry lab before. Okay. almost done. We're on oxidation and reduction reactions now. So oxidation is loss of electrons, reduction is gain of reductions of electrons. I'm sure you've heard of I'm forgetting the mnemonic for it. So this is the mnemonic that I was forgetting. Oil rig, oxidation is loss, reduction is gain. That's kind of helpful for me. Okay, so with respect to oxygen transfer, oxidation it's very helpful to know that oxidation is gain of oxygen, which kind of makes sense, and then reduction is loss of oxygen. An oxidizing agent and a reducing agent, it's really confusing how these work, but basically an oxidizing agent helps other things get oxidized. So oxidizing agents gets reduced and reducing agents gets oxidized. Now we have oxidation rules, and oxidation rules is is basically how do you determine what the oxidation of something is in a compound. So if I have like H2 PO4 minus, right? The oxidation rule will help you figure out what is the oxidation number for each of those. Like H would be +1, then P you can figure out, oxygen is going to be -2. And so you just kind of have to walk through these and understand, like, okay, this is free elements. So if I just have like, I don't know, Na, then that's just going to be 0. If I have Na plus, like a cation, that's just going to be +1. Group 1A metals are going to be +1 when they're in compounds. Group 2A metals are going to be +2. Group 7A in compounds are going to be -1 unless they're combined with an element of greater electronegativity. And then H is going to be usually +1 unless it's like paired with a less electronegative element, then it's -1. O is going to be -2 unless it's like H2O2, in which case it's going to be -1. And then the sum of the oxidation numbers, this is really important, must equal the overall charge. That's what's going to help you the most. Okay, now we're on net ionic equations, or let me go through balancing half. Actually, let's do net ionic equations. So net ionic equations is basically, let's say I had like some spectator ions. So Na plus, let me show you an example. So this is an example of how we find like the complete ionic equation and the net equation. So you see all these aqueous things, right, that are reacting, and out of those aqueous things we actually get a solid, but then we get these other aqueous ions, and so these aqueous ions actually cancel out because there's no change. They're still aqueous, we haven't changed anything, and so basically this is going to be our net ionic equation. That's how you can think of that. So that's net ionic equations. You ignore spectator ions. Spectator ions don't do anything. There's complete ionic equations, which shows all the ions. You have disproportionation reactions. Not too important that you know this, but it's a type of redox reaction in which an element both is oxidized and reduced. So you can calculate the oxidation states, and you can see like, oh, this oxygen both got oxidized and got reduced. So you can see like in examples where oxygen is like a 0 and then it becomes a -1 and a -2, or sorry, let's say there's H2O2 and then somehow it forms just normal oxygen, which is a 0, and then it forms like H2O, which is a -2, right? So then in that case it's been oxidized and reduced. I think my math checks out there. Then we have redox titrations. It's very similar to acid-base titrations, but these titrations follow transfer of charge rather than transfer of, protons or just pH changes. Then we have potentiometric titration. Again, not too high yield, but you just use the voltmeter to measure the electromotive force of a solution. Instead of using indicator, equivalence points, or sorry, instead of using indicator, you use the equivalence point, but here it's determined by the change in voltage rather than using like an indicator or measuring pH. Okay, now we have balancing via half reaction method. So here you take both the half reactions, and let me show you an example. So this is kind of a context in which you have like, what's happening, like chromium, this is the change in chromium, this is the change in iron, right? But you know that there's some loss of electrons, gain of electrons somewhere. You know that there's like one of these is getting oxidized, one of these is getting reduced. So you split them up into half reactions, oxidation half reaction and reduction half reactions. And then if you follow the steps, you can actually figure out the full equation for this. So you know that we added protons and we added electrons and then we added water, And basically now the reaction is all balanced out. And so we wouldn't have been able to figure that out just based on this equation. But using that whole method, we found out what is the actual reaction with all the electrons and protons that are getting exchanged. What is going on? So just follow the steps and you'll be able to balance half reactions. Okay, now we're on the final step, which is electrochemistry. And this is honestly probably the toughest page on this in this chemistry portion. I always had trouble with batteries and how they work. So let's talk about galvanic cells and electrolytic cells. Galvanic cells is where you have like a reduction and an oxidation part of this, and based on the anode is where oxidation is happening, and the cathode is where reduction is happening. And so oxidation, remember, is loss of electrons. So the electrons go from the anode and go to the cathode. And this solution has Cu2 plus. And then the Cu2 plus combines with these electrons that are going here and they form copper, right? And so what you're going to find is that this is actually going to gradually get thicker and thicker because more of this copper solution is becoming solid copper and joining with this bar. And what you're going to find here is that this is actually going to get thinner and thinner because this zinc, solid zinc, is going into the solution and just becoming zinc 2 plus. And these electrons are going this way. And then you have a voltmeter that just calculates what is the voltage that is being created by this solution. You also have a salt bridge, which helps balance out the charges. So you have, this solution, you have all this positive copper that's going into here, and so you have negative sulfur that's going away from here. Here you have all this positive zinc that's going in here, the zinc exchanges, and you get some sulfur that's going here. So that's kind of a galvanic cell. Electrolytic cells is just basically very similar. It's just that you have a battery in the middle, and so the battery is forcing this electron flow to go to the opposite direction. And so it's important to know that anode is still the same thing. It's still the place that's oxidation is happening, and cathode is still this place that's reduction is happening. So here it gets kind of confusing, the definition, but as long as you know, okay, oxidation is happening here, there's loss of electrons, that's the anode. Here there's gain of electrons, that's the cathode. That's all you have to remember. So that's kind of the difference between electrolytic and galvanic cells. Okay. Electron flow happens from anode to cathode, like I just mentioned, and then current flow, if you watch the physics section, I talk about how current is kind of interestingly named because current always refers to the flow of positive charges. So if electrons are flowing here, then that technically means current is flowing the opposite direction. Galvanic cells is what I just talked about, spontaneous reaction, negative delta G. And then we have this new concept which is E, and that's basically the same thing. It's representing the same thing as Gibbs free energy. It's just more specific for a battery or electron situation. Now, electrolytic cells are non-spontaneous, positive delta G. So like Gibbs free energy, it's kind of non-spontaneous reaction. Okay, now we have concentration cells, and concentration cells are just specialized forms of galvanic cells in which both electrodes are made of the same material. And it's actually just the concentration gradient between the two solutions that causes a movement of charge. We have rechargeable batteries, and rechargeable batteries just experience changes in the situation between electrolytic and galvanic states. Now we have these, and they're not too high yield, so I'm not going to go too much into it, but we have lead acid and then these two, and again, not very high yield. They're just like very specific types of batteries, so I'll let you read into it. Okay, now we have cell potential. So cell potential, there's reduction potential, and reduction potential just quantifies the tendency for a species to gain electrons and be reduced. So something that is usually really willing to accept electrons, that has a high reduction potential. If it does not really want electrons, or usually it wants to give away electrons, then it has a low reduction potential. So a standard reduction potential, that's what this is, right? And it's basically, and this is E reduction, and basically it's just a chart that tells you like, okay, this is very high on a reduction potential, this is very low on a reduction potential. So if you imagine like you wanted to create a galvanic battery and you have an anode and cathode, what material would you want to use for the cathode and which one would you want to use for the anode? Hopefully you're thinking like for the cathode is where reduction happens, so I want something with a high standard reduction potential for the cathode, and I want something low standard reduction potential for the anode, because the anode is where oxidation happens. And the way that I always remember this is that anode starts with a vowel, and so does oxidation. Cathode and reduction, those don't start with vowels. Okay, now we have standard electromotive forces. So this is just the difference between the standard reduction potential of the two half cells. So if we subtract the reduction potentials, that's what we get. And then we know that we just went over this. Okay, now we are into EMF and thermodynamics, and it's just important to understand like these two are very related. It's just the opposite signs. So this and this, basically, there's in this equation there's a negative sign, which is kind of unfortunate, makes things confusing. But basically, when this is positive, that means it's spontaneous, and when this is negative, that means it's non-spontaneous. Okay, I would really try to know this equation over here that just that's just like the relationship between Gibbs free energy and this E of cell value, and that is a very high yield relationship. And these are equations that we already talked about in relationship to Gibbs free energy. This is important also. 1 coulomb is equal to a joule over a volt. Okay. Finally, we're on Nernst equation. Nernst equation is just describing this relationship over here, and this should make sense if you understand the relationship between delta G and K, like we talked about before. But basically, that's just describing the same relationship. So if you understand the relationship between delta G and E, then you should understand the relationship between K, Q, and E. So if K, Q is greater than 1, then we should have a positive E. If K, Q is less than 1, we should have a negative E. And if it's equal to 1, then this should be 0. And then this is a very important equation that just relates the Q value. Remember, the Q is about how much concentrations do we have in our equation, and the E of the cell. And based on that, you can figure out like, oh, does this want to move does this want to move in this direction or in this direction? And that's kind of what you can figure out based on this equation. And then if we take what we know, which is the R value and the F value over here, and we simplify it, then we get this over here. So that's kind of what that's doing. All right. That's the entire chemistry section. I really hope that this was helpful to you. If you have any questions, feel free to leave a comment down below or send me an email. Thanks so much for watching. I really appreciate your time. Bye, everybody.